As you have noticed so far, different block ciphers has different number of rounds. For instance, DES has 16 rounds, but present has 31, and AES has 10, 12, and 14 rounds depending on the key size. So a natural question to ask is how many rounds a cipher should have. Unfortunately, there's no direct answer. Actually, there's not much of a scientific answer to this question because as we have discussed, confusion and diffusion are abstract concepts. We cannot measure them. So we cannot be sure how many rounds are good enough in terms of confusion and diffusion. So the common belief is that increasing the number of rounds increases the security. This is not always true, of course. Against some kind of cryptanalysis techniques, yes, this works. Increasing the number of rounds increases the security, but we have some cryptanalysis techniques that works regardless of the number of rounds. So if you have that kind of a weakness in your design, increasing the number of rounds would not help you. But increasing the number of rounds will decrease the performance. So there has to be a trade-off between performance and security. So you have to decide what is enough for you. So a common practice is as follows. Designers apply every known cryptanalysis techniques, and if they can break n rounds of the cipher, then they choose the round number r as r greater than or equal to 2n to stay on the safe side. So you double the number of rounds that you can break. This is actually kind of a good approach. I mean, if you can break n rounds and then design your cipher as n plus 1 or n plus 2 rounds, attacks always get better. People come up with new ideas and improve the previous attacks. So in such a scenario, your cipher might get broken. So a common technique is to, as I told now, break as many rounds as you can, then double it and choose the number of rounds greater than equal to this number. There are many standardized block ciphers. In terms of NIST, there's actually 2, AES and triple DES. There's also the third one, skipjack, but it is for legacy use because it has 80 bits of key, and NIST does not suggest use of 80 bits key. NIST suggests that your key size should be, your security should be at least 112 bits. This is the security of triple DES. And anything less than that number is not supported by NIST. So skipjack is not a current standard. ISO has more standards, 2 for lightweight. NIST doesn't have any standard for lightweight, but as I told you, there's a competition going on. And probably in 2 or 3 years later, NIST will choose at least one winner, maybe multiple winners, and those will be standardized by NIST. But these algorithms are authenticated encryption algorithms, so they're not simply block ciphers like in this picture. So ISO has more standards. Height is theoretically broken, but others are good to be used. And as far as I know, none of them has any patents, so they are free to use. So far we have discussed the basics of block ciphers, let's say. We have main definitions and idea behind it. But even at this point, many problems arises. First one is key management. So in block ciphers, but also in symmetric key cryptography, secret key must be exchanged between the communicating parties before they can use the block cipher, because we are assuming that we are communicating in an insecure channel, so we cannot transmit the secret key in this insecure channel. So to communicate with n people, one has to securely exchange n keys, and if n is a huge number, this is not practical. So the answer to this question is, thanks to invention of public key cryptography, you can use public key encryption algorithms like RSA. So you can communicate with people with whom you haven't exchanged secret keys before, but they are slower than block ciphers. So you have performance or bandwidth issues in this case. A second solution is, this solution comes from public key cryptography. You can use key exchange algorithms like Diffie-Hellman key exchange, and with this algorithm you can agree on an AES key with somebody you haven't talked before. So with this, with this solution you can do any e-banking or e-commerce on the internet. A second problem that arises by the use of block ciphers, but actually this is valid for almost every encryption algorithm that uses a secret key. So problem is key storage. Storing keys directly on the hard drive or memory can be a problem. In case of a Trojan, then this key would leak. So actually this is a problem that cannot be directly solved, but one of the common practices is to use USB dongles in case of very important keys. Third problem is the message length hiding. Plain text and corresponding ciphertext lengths are identical. So in symmetric key cryptography, if you encrypt a 1 megabyte of file, the ciphertext is also 1 megabyte. If you are encrypting 120 bits, 28 bits, the ciphertext is also 128 bits. So if the adversary knows the context of the communication, then they can guess the plain text just by the ciphertext length. So here's an example. For instance, some websites encrypt the forms filled by the users, but the remaining parts sent unencrypted. An example from a medical form, for instance, the question could be like, did you ever have a surgery? If yes, provide details. So your answer will be encrypted. But if the user's answer to this question provides a short ciphertext, namely one block, then most probably that the answer was no. Because if it were yes, then you will provide details, so your answer will be longer, which means that your plain text is longer, which means that your ciphertext is longer. So just by looking at the ciphertext length, a person who is listening to this communication can guess your answer. So this is valid for this problem is valid for block ciphers and stream ciphers. A solution is adding random bits to the plain text before encryption to hide the message length. Of course, this solution causes more data to be transmitted. A few years ago, we had work on this topic. You can look at it if you're interested. But adding random bits at a random length can somehow hide your message length, and this way can provide you more security. Fourth problem is key generation. So in all of these slides, I mentioned that we are using secret keys. For instance, DES uses 56-bit secret key. Present can use 80-bit or 128-bit secret key, and so on. But the question is, how do we generate these secret keys? As you're familiar, in daily life, actually, you are using these encryption algorithms all the time. Even when you're listening to this video, probably you're connected with HTTPS, so you are using AES encryption, but you haven't chosen any key by yourself. So the computer, your browser, does this for you. So question is, do they do it in a correct way? To obtain k-bit security, the k-bit key should be generated randomly. So randomly generating bits is an important security problem here. And we will be talking about this actually in the week when we talk about randomness. But solutions are cryptographically secure random number generators, or you can use password-based key derivation algorithms, which we will be talking about after hash functions. So before moving on to next week, where we will be talking about block ciphers in depth, I want to give you some thinking exercises. These are important exercises. First one is as follows. You are given a dice and you are allowed to roll it to see the result as many times as you want. You are asked to determine if the dice you have is a fair dice or it is a biased dice which rolls 6 with probability 1/3. So what would you do to decide which dice you have? So we are asking you to distinguish the dice you have between a fair dice and a biased dice that rolls as 6 with higher probability. Your answer to this question is very important because uh, actually many cryptanalysis attacks actually are statistical attacks. So many cryptanalysis techniques are statistical attacks, and there we are actually trying to find the statistical weakness in the cipher, and we use it as a distinguisher. So your answer to this question, where you're trying to find a distinguisher for a dice, actually is the main idea behind cryptanalysis techniques like differential cryptanalysis or linear cryptanalysis and so on. So you have to think really hard for this question, and you also need to think if your solution is a good one. I mean, you have to try to measure what would be your success probability. Second exercise is how many people we need to have in a room so that we have 2 people with the same birthday with probability greater than 1/2. This is an important question, which we will be using for the collision resistance of hash functions. So this is also known as the birthday paradox. Most people think that the answer to this question would be really large, but the real answer is really small. This is why we call it a paradox, actually. But you can, by using pen and paper, you can calculate this probability easily. It is not that hard. So I suggest you to think about this question and these 2 exercises, and I encourage you to find your solutions by yourself.